And then this again is the contraction estimate, and the whole proof now actually with all these intermediate pieces sort of fits on 2 pages. I'm going to skip that just in case you're interested in that. Okay, so if we have a priori L infinity estimates for the continuous discrete problem, we have quasi-optimal linear approximation for this semi-linear class of problems, and then we have contraction and optimality for the adaptive algorithm that we use. So how do we actually solve the discrete equations? I'm not going to say any more about this, but basically we use things like BPX and stabilized hierarchical basis methods. We have a couple papers on that. And the way we do things in parallel is using these algorithms that are the class that Scott Baden talked about yesterday. So I'm going to skip this discussion to get to this relativity problem that I think will be interesting. Okay, so let me say a few words about this elliptic problem. It's going to turn out to be semi-linear, and it's going to fit into this framework. But I have a few slides that's going to take us a little bit to get to that equation. But I think you'll find it interesting. So this is a problem I've been working on for a while. For maybe since 2000, 2001, I sort of wrote my one paper, sort of started my thinking about this problem after a sabbatical at Caltech. So basically, the idea here is, people are very interested in relativity right now because they just built, the physics community just built several very expensive gravitational wave detectors. Gravitational waves are predicted by the Einstein equations to basically be emitted by interacting massive objects floating around the universe, things like neutron stars and black holes. When they interact with other large masses, emit gravitational radiation. And the Einstein equations are basically just a constrained hyperbolic system that describe the wave emission. And so you can understand this set of equations and then this resulting elliptic system that I'm going to talk about by thinking about, sort of intuitively thinking about the way gravity is described geometrically by Einstein. And so this is the way we experience Newtonian gravity. You have a heavy mass, and you have a light mass. The light mass is attracted by the heavy mass according to sort of Newton's law of gravitation. But what Einstein said was this is really just our interpretation of a geometrical effect. That if you have a large energy and or matter density in space-time, then it deforms space-time around it, and then a small mass just goes on a straight line in its normal straight line trajectory, but it appears to us to be deformed because this mass is actually moving on a curved surface. I just drawn the space deformity here, but it also deforms time. And this exact deformation, both in space and time, is described by a particular partial differential equation system called the Einstein equations. These are pictures of the 2 detectors that went online several years ago. They haven't detected anything. They were very expensive. I think the US project for LIGO was something like $400 million. It was, well, I think it is the most expensive NSF project right now. And there are a few detectors around the world. There's a couple in Europe, and there's one in Japan. I'm most familiar with the LIGO project. So the LIGO project, they're very interested in numerical simulation of the Einstein system, because what they want to be able to do is when they detect a waveform emission, it's basically a laser interferometer that works very much like the Michelson-Morley interferometer. Basically, a gravitational wave comes through this region of space-time, and it creates phase changes in the lasers that are shooting back and forth between some mirrors in each of these arms. And they'll be able to detect a gravitational wave through looking at these phase shifts. And these 2 detectors are located on different parts of the surface of the Earth, so they'll be able to triangulate where the source is. But to actually understand the source, they need simulations of the wave emission. So there's a very large interest in the physics community in simulating the Einstein equations, and this is actually how I got interested in this. Okay, so what's the Einstein system? Here's my 1-slide introduction to the whole thing. It's not that hard to understand what the equations are, at least from a sort of a big picture point of view. So you have basically you're trying to describe something that's curved. You have a differential equation for the curvature, and you also have differential equations for matter fields that are happening in this curved space and time setup. So you can understand the Einstein equation just by looking at curvature a little bit here. So if we think about normal partial differentiation of a vector field, and just using the shorthand notation here, the common notation, in this way, what we know if things are smooth is that differentiation commutes when we're on a flat surface. So if we're in an open set in RD, things commute. But if you look at what happens to covariant differentiation, so covariant differentiation being the semicolon notation here, being that the way we have to differentiate vectors and tensor fields on a surface in order for us to get a tensor back. So it's basically a modification of partial differentiation that it's a particular modification involving a coefficient called a connection coefficient that transforms in a particular way in a chordate transformation. So when you look at this, two of these guys don't commute, and what's left over, if you collect all these symbols together, these affine connection coefficients, you get what's called the Riemann tensor. These guys you can write down if you have a smooth symmetric two-index tensor that describes the way you measure lengths on the surface, so a metric. Then these guys you can show can be produced by differentiating particular linear combinations of derivatives of the metric. So these guys you can actually write these down for a particular surface, and in that case they're called Christoffel symbols. So these end up being basically linear combinations of first and now second derivatives of this metric. And this is the basis for the Einstein equations. The Einstein equations are just taking this object and taking a particular sum on some of these indices that appear here. And this particular object G, the Einstein tensor, is just a particular linear combination of this metric and then this linear combination of first and second derivatives of this metric. Space and time are sort of all mixed together here, though, because this metric is a space-time metric. T is the matter-energy density tensor. And of course, the way we like to think about P to E here is we like to think about you have initial data on a space-like surface, and then you have some evolution equations that propagate the initial data forward in time. And you can take the system and take the space-time manifold that's representing the universe and come up with a space-like foliation where each slice is space-like, and there's a well-defined procedure for doing this. And this is all formalized in Hawking and Ellis's book and in more recent literature. But in particular, if you have what's called a globally hyperbolic space-time, you can construct a sequence of Cauchy surfaces which are space-like and give you a well-defined initial value formulation of the Einstein equations. And so I've just drawn a picture of this. And then what the evolution equations then propagate are the spatial metric on the surface and something like its time derivative. It's not free evolution, though, so very much like Maxwell equations, you get constraints, and in particular you get two constraints here. This one's referred to as the Hamiltonian constraint because it has to do with energy, and this one's referred to as the momentum constraint because it has to do with momentum when you look at a Hamiltonian formulation of the problem. Turns out this is all fits into a Lagrangian. You can derive the system from a Lagrangian. In fact, there's a Hamiltonian formulation that uses this foliation setup. So this all has a nice geometrical structure. This system of constraints is underdetermined, and basically there are four equations here. This is a single equation. This is actually a vector system of three equations. But if you look at all the free pieces of data, there are actually 12 pieces. So you have to specify 8 using some procedure, and then you determine the other 4 from these two equations. And the most common way to do this is to use what's called the York conformal decomposition, where you fix a background metric on a space-like hypersurface and then fix a couple of other quantities. And then you recover the spatial information, so the metric and its time derivative, using these transformations. And when you do this, you produce this system. So finally we have the equations that I'm after, and in particular I'm after this one. So this is a semi-linear problem where there's a linear piece. This is the Laplace-Beltrami operator, so it has a metric in it, a spatial Riemannian metric. It's not a positive definite metric. And this is just the scalar curvature corresponding to the 3 metric. So it's like you take the Riemann tensor for this 3 metric and you fully contract it, and you get that constant R. These two guys together are called the conformal Laplacian. And then I have this semi-linear term. It has some nasty pole-like terms. So if I go through 0, I'm in trouble because these guys blow up. And then I have what turns out to be a critical exponent for space dimension 3, which is what we're typically in here. So this is a very sort of nasty kind of semi-linear problem. And then it couples to this linear equation for W, although it couples in a nonlinear way to the other equation. So this system is referred to as the Einstein constraints, the Hamiltonian momentum constraint. This is just some notation for this second order differential operator here on W, symmetrized gradient operator. And this is kind of an alternative notation for covariant differentiation. It's used in the literature quite a bit. As I mentioned, these affine connection coefficients can just be built for giving you the differential structure here from the space metric, just linear combinations of the space derivatives.